Okay. Good afternoon, ladies and gentlemen, or good morning, depending on what part of the world you are. Welcome to our webinar today titled Validating Translation Quality and Document Revision Changes. Today we'll demonstrate a solution for engineers, quality organizations, and anyone who needs 3D information from a variety of CAD formats that are common to automotive and aerospace suppliers. So a few questions here. Do you struggle with revision changes, understanding what has changed from version to version? Do you need the ability to easily translate to validate translations to meet quality requirements? Do you need the ability to easily overlay point cloud data with CAD data and determine differences? Do you need to deal with multiple CAD formats? Are you struggling implementing model-based definition, commonly referred to as MBD, processes internally? And do you need simple quoting and estimating tool that will open any CAD format? The solution we'll demonstrate today provides these capabilities and more. In addition, we'll demonstrate the ability to create IGES and STEP directly from the solution that uses the native CAD kernel. So in terms of the agenda today, we'll go through just some quick introductions. I'd like to take one moment and introduce our organization, Adaptive Corporation, and then we'll introduce the solution today, which is a product called MagicCheck by a well-known data translation vendor by the name of TransMagic. They've been in business for a number of years, followed by a demonstration, and then we'll have wrap-up and Q&A at the end of the presentation as well. So in terms of introductions, my name is Frank Thomas. I'm with Adaptive Corporation. We're joined today by Craig Dennis of TransMagic. Also, just a word about the user interface and interacting on the webinar today. Many of you are probably already familiar with the interface, but there is a chat window in the upper right-hand corner of your screen, and that can be used in the event that you have any questions that you would like to ask of the panelists during the webinar. Feel free to type in any questions as they occur to you, and then what we'll do is we'll queue up those questions to be addressed during the Q&A session at the end of the webinar. So once again, if you have any questions throughout the webinar, feel free to type them in as they occur to you, and we'll make sure that we do our best to address your questions. So to briefly introduce Adaptive Corporation is a Dassault Systems sales and support organization. We offer the full portfolio of Dassault Systems products, including CATIA, Innovia, Dalmia, Simulia, and 3D Via. We specialize in data management solutions for engineering and business processes. Adaptive Corporation is a consulting-focused company committed to the success of our customers. We partner with our clients to enable innovation and streamline processes. Adaptive works with a variety of technology partners like TransMagic to bring a portfolio of best-in-class products to our customers. We're deeply committed to superior service and training to maximize your technology investments. In addition, Adaptive has a metrology organization that works with automotive and aerospace companies in support of their quality initiatives, including AS9102 and PPAP. We provide first article inspection software that operates natively in CATIA V5 and or PDF. So at this point, I'd like to bring on our presenter today. Our presenter today is Craig Dennis of TransMagic. Craig is the Chief Technical Officer of TransMagic, so he's one of the chief architects of the solution that you're going to see today. And once again, Craig will briefly introduce their organization and then get into a live demonstration and show you a number of examples as part of the demonstration. So with that, Craig, over to you.
Great, thank you, Frank. And pass control over to me. There we go. Show my screen. And my presentation. Okay, thanks also, folks, on behalf of TransMagic for attending today. What I'd like to get started with initially is just a couple of slides so you know who TransMagic is if you haven't heard the name before. And then the meat of the presentation will be an actual demo, which I prefer, and I suspect many of you do also. So about TransMagic, we were founded in 2001, so we've been around a number of years. Our initial development focus and goal for the company was to develop 3D interoperability, repair, and more recently validation software. We have a very comprehensive translation and repair engine that we have based our current product that I'll be demonstrating today, MagicCheck, on top of. Our function has, our focus has always been on quality, ease of use. One thing that's unique to TransMagic when you're bringing in CAD data, native CAD data or even translated data, but primarily native CAD data, and this is in terms of translation or validation using MagicCheck, we have a unique approach in that we license the APIs from the CAD vendor. So under the seat of TransMagic or MagicCheck, depending on what software you're running, there is a seed of all of the kernels that we license. So that could be CATIA v5, CATIA v4, ProE, NX, Inventor, SolidWorks. It's a native access, and so that enables our validation software to be very, very high accuracy. We are from Denver, Colorado. I'm based in Denver, Colorado, where most administration and some development is done, and most of the development is done in the U.S. and international. So a brief background on our existing TransMagic technology. So again, from the very founding days of TransMagic, we created a very comprehensive and flexible engine for translation and repair of native CAD data using the native CAD kernels, and also as it outputs to generic kernels, so could be ASYS or Parasolid, STEP, IGES, JT. We have support for all of those varieties. Our interface is very high level, no expertise required, with the ability to drill down. This has always been a hallmark of TransMagic for the hardcore techies. You always have the ability to go and dig deeper into the interface and get the more detailed information that you may be after, but basic usage is going to be very high level, which means it's very accessible to a wide audience. So recently, and as part of our product offering, we've created a geometry compare and validation software, and this is called MagicCheck. What is great about MagicCheck is it's built on top of that TransMagic foundation that's been around a decade. So it's very mature, very high quality, high performance, profiled code, and then MagicCheck is a set of new functionalities on top of that. And so, the question has often come up, what is MagicCheck? What does geometry have to do? Geometry translation and repair have to do with QA. There's many answers to that. For one, it's our specialty. It's solving a very complex problem in a very easy way, and we think the validation and revision control is one of those areas of engineering that is a difficult problem in need of a simple approach, and so that's kind of our specialty, is making those types of things simple. The expertise is certainly in our wheelhouse, geometry and translation, repair, analysis. These are all things that we are very familiar with, and the expertise is also in our warehouse. So we're well suited to deliver this type of technology. The main reason, though, is as of recently, our customers have been asking for it. One of the main aerospace vendors out there have really, they're a TransMagic user, and they really recommended we did this with the help of Adaptive's consulting. I think we've delivered a very high quality product. And so getting into MagicCheck, these are the things that I'm going to show today. It's primarily composed of three core areas in sort of the QA space. And the first one is point-to-part. This allows you to bring in the native CAD data, or of course generic formats, IGES, STEP, JT, etc., and then also a point set that you've acquired either via laser scanning or CMM or what have you, and compare the points to the part. And they may have a variety of different uses to you. It could be to refine your molding process, to see where maybe molds are wearing out. Whatever the need is, that's the core function set. It allows you to detail inside points, outside points, your inspect points, and we'll get into a broader scope demo of that here in a second. The other main portion, there's the other half of the application is called part-to-part, and there are two pieces of part-to-part. This is where you compare two parts. Number one is validation. So many of the specifications, such as the AS9102, will require you to at least catalog that if you are using a translated file from the original authority data along any point of your process, that you are storing reports that essentially prove that the translated data you're using in your process is within specification to that authority data. Again, many quality programs require this type of reporting, or at least cataloging of information today. So here's a snippet from the Boeing DPD spec DS51991 regarding translations. This is the latest Rev J. And so typical allowable deviation tolerance is 1/10 to 1/1000th, and we'll show you how you can change that and check against those tolerances and produce a report. The other handy tool in terms of part-to-part analysis may not be in geometry validation. This may be where you know that there's a change. You're expecting a change. It's revision A to revision B or B to C, etc. And so we call this revision management. It's been called revision control. Essentially, though, it allows you to very quickly identify what's changed in a part. Some of the applications for this could be, a large job shop spends 40 hours programming tool paths for one specific part. Their vendor sends them a new revision, and they say, here, program it for this particular part. Nothing may have changed. It could be one piece in a larger assembly, and instead of spending another 40 hours reprogramming for something that hasn't changed, this revision management software will very quickly allow you to find the change regions and determine if you need to do any reprogramming at all, and if so, maybe very little. Also, any of these functionalities you can generate a report from that you can catalog and store. And so I will show you the reporting mechanisms. The reports are very similar but slightly different for point-to-part and the two part-to-part styles, revision and validation. And with that, I'll get started with an actual product demo. And again, please do capture your questions, and I'd be happy to answer those. So let's launch TransMagic. So this is the latest version of our software. This is TransMagic R10, and what we're seeing here on the right-hand side is our MagicCheck tab. Again, MagicCheck is based on the TransMagic foundation, and we will show you a little bit of translation and repair at the end of the demo, but primarily we're going to focus on MagicCheck, which is point-to-part and part-to-part. So first off, let's just go from left to right. We see we have this little ribbon bar. Notice the interface, very contemporary and high level, one of our targets, of course. So let's start with a point-to-part, rather. And go to my adaptive folder here. I'm going to do 3 different styles so you can just see some of the functionality. One is going to be just showing you how to generate a point-to-part report and a very simple analysis. The other will be removing some noise, and the other will be refining a large data set to make it more manageable. So what we're going to do first is open up a CATIA V5 part. And again, under the hood of TransMagic, we are actually firing up a seat of CATIA V5. So you're looking at native data being brought into our environment. This is a very simple aircraft panel. One of the things that you need to do initially is set up your tolerances, and that's this button over here. So what I'm going to do is just, I think the default is 5/1000ths. I'm going to test against 1/1000ths here. And I believe we're okay. Now, one thing you'll notice about many point formats, and honestly I can't remember on this one, is you need to know what units you were acquiring the points in. I believe this one is inches, but it very well could be millimeters, so we're going to find out together. The other thing that you'll need to do to set up a point import is many files, many native CAD files, have the ability to store what we call a WCS. This is a working coordinate system. This is sort of the datum where the point was measured. This particular example, it's a real-world customer file, does not have that. So what you would need to do is have established your measurement datum, and you can key that in manually here. This one just happens to be at the origin, the same as the CAD origin. Now we're going to import points. And so here we have a CSV file. And what you'll see is we have this little generic point import format. We support all of the varieties of point import formats now. So it could be an STL, could be IGES, could be STEP, Excel spreadsheets, CSV, DMIS files, etc. But if you have perhaps maybe a homegrown point format that you use, and maybe you manually came into a spreadsheet, one nice little feature here is that you can map the fields. So even if we don't know the format, as long as it's ASCII readable, what you can do is, and comma separated values or some sort of delimiter, you know, a semicolon, a tab, or whatever. We'll be looking for all of those things. You can simply say, here's my name. The 4 fields we care about are your point name and your X, Y, and Z position for the point. And so here, there is no name. This point format just has X, Y, and Z, so this is being assigned to these columns. We already support this one, so it automatically fills that in. And okay, here we are. Good. So it was in inches. And what you see now is our point set. So it's a very simple defined coordinate measurement point acquisition here. So the first thing we're going to do is before we generate our analysis, let's take a look at our user input dialog. We're ultimately going to generate a report. So one of the things you'll want to do is open up your user input dialog. I'm just going to leave the defaults here, but you got your company name, your office location, address. You can delete all of these fields if you want them, or you could keep them. Company logo. Here you have space for inspector name, part name. We'll fill in a lot of this information. So the part name, you know, we actually auto-fill in. This form allows you to add any number of fields. So let's say this is part of a bigger project, then you can add new fields and insert additional information that's specific to your process, or delete any of this information if it's not specific to your process. So you'll want to create your form there. And now let's run an analysis. That's as simple as selecting on the part and clicking the Analyze. And again, we're going to check about those top values and lower values. So max profile tolerance, that's reflected here on the right-hand side. That means a measurement is outside of the CAD model, outside of that solid volume. And we're also testing for the minimum profile tolerance. So this means we're checking for points that are inside that CAD volume. And that is reflected in this little legend here on the right-hand side. So we have what we found here. Most of these points are all within tolerance, but we found several that are on the outside band and several that are on the inside band. And so the blue ones and the various gradients here reflect the outside, and inside for the other orange to a red. So now we know where they are. Let's start looking at how far they are actually off. So for this, we're going to open up our point browser, and this gives us all sorts of information and ways to tailor our data. First off, let's just say, and I'm not presuming that this is part of your process. I'm making it up here myself. Let's say we're going to select all of the in-spec points. So this means all of those green points that are actually in spec. What we can do is we can actually delete those if we want. If we don't want to include those in our report and we want to get rid of them, you know, for this session anyways. Or what I'm going to do is I'm just going to say exclude points. And so one thing you'll see is now all the points disappear from my display. They're still there if I want to enable them, but I don't want to include those in my report. I just want to include the inside and the outside points. We can show point labels, and so these labels were contained in the point file, or I can show my deviation value. One thing you'll see is the outside deviation, since the points are actually on the outside of the part, they're drawn right above the points. You'll see the inside points, depending on how far inside, they start to cut off my numbers here. So what I'm going to do is generate a couple of views from my report that allow me to see these inside points a little differently. So now we have our points. Let's generate some views for our report. We know how much they're off. We're going to also include all of these values in our report, but let's generate some views. So we'll call this outside view 1. Anytime you want to capture a view, you simply just hit Add New View. That inserts it into our view browser, which we're going to get to in a second. So let's say we'll call this point group 2. And notice how we can see the number here. We can't see the point. What you can do is on our View tab, you can change your rendering mode, and this will be captured. Any view that you captured, you can see reflected in your rendering mode. So for this, just so we can see this point here, we're going to go wireframe mode, and maybe to make it a little more clear, let's just turn our background white. Maybe that's a little too much. We'll do an off-white there. And so let's capture this view. And I'm just simply trying to generate different view properties so you get the feeling that you can capture all sorts of different view properties, which is true. So let's zoom into this region here, and let's do one more view style. This is sort of our drawing our mesh here, and let's just change the background color. You can turn on shadows. We'll turn them off for this case. And let's capture this view. So now what we're going to do, zoom out, go to our view browser. Notice one thing that we populate automatically, you have the option to turn this off, is all of the default views, top, front, right side, ISO, etc., etc., etc. So I'm gonna suppose that we don't want all of those. Let's include this isometric view, but let's just turn all of these off. It's as simple as a mouse click. Uncheck the box, so you can always turn them on, but right now these are the only views that I'm going to output. So I've got my default isometric, and I've got my view 9 here. So let's rename this. We'll call this outside points 1. We'll call this view 2, and we'll call this one view 3. And again, take note of the rendering properties being stored. We'll call this inside points. And I'm just simply giving it as random names so that you can see them in your report output. So we've brought in a part, we've brought in the points, we've populated our user input dialog, which again just gives information about the job and the person doing the report. And now let's create the report. So we have two different styles or two different types, and that's an HTML or an Excel spreadsheet. We are currently in development of a PDF translator for a variety of reasons, and one of those will also be the ability to generate a PDF report of this point-to-part analysis. But for now, let's just generate an HTML file. Let's put it on our desktop here. And so you'll see it capture all of those views, or insert all of the views that we captured. All right, and let's take a look. Here's my report. And so this is our point-to-part analysis report version of the product. We have hyperlinks here in the Excel spreadsheet. These would be tabs. So if we go immediately down to the measurements, then remember we excluded all of those in-spec points. So we really don't have a lot of points here, but they're tied to the legend, inside, outside, the actual deviation, etc. Let's go back up to the top again. And we have this little sort of default dialog here that gives us all the pertinent information, the tolerances we checked against, how many were out of tolerance, the max and mins, etc. Here's our part name, and you might put your part number. Any of the custom fields that you would have put would have been inserted under this in this category up here. So this could end up being a very extended view if you insert a lot of information. And then you've got your default views that we specified. So here's our isometric. You know, here's our outside points 1, view 2, and then inside points 1. So there you have it. And then, of course, on the second page or another tab in the spreadsheet would be all of our list of points. So that's kind of a quick report output and what to expect. So let's get into the other point type. So I'm just going to delete that. Here we go. So this one we're going to filter out a little noise. Again, we're going to bring in our V5 part. This one has also this working coordinate system. This was included in the part and used in the CMM software. And so that's what this little XYZ looks like. That's our coordinate system that we've measured these points against. So we still need to set that though because it's not at 0, 0, 0. So we'll hit set, and we support that coordinate axes for all of the native CAD formats. The neutral files typically don't support that, so STEP and I just actually doesn't have that. So if you use that as your CAD part, your geometry part, you'll have to key these values in. But what's nice, if you do have this, we just hit pick, and notice how all of our values update here accordingly. And I noticed that they've come in at 0.039, which is my reminder that the point set was measured in millimeters. So let's go over to our settings here, change our point import to millimeters. If this is included in the point file, we'll automatically set this, but most point files do not include the units of measure that they came in at. So let's import our points. Oops, I'm sorry. I've meant to expand that one more time. There we go. Set our coordinate system and import our points. And I'd already set that for millimeters. Notice this one has a lot more, many more fields. And so we already recognize this point format already, so they're automatically populated. And now I'm going to zoom out. There we go. And so let's run our analysis. Same thing. Click on the part you want to analyze. So this could be a multi-part, assembly or a multi-body, and you just pick the part you want to test against. And here we have our points. So immediately I noticed something odd about this. Number one, there's no inside points. That's not odd, but they're only outside. But they all seem to be isolated here around these holes. Let me turn off my axes there. And so really what we have here are hole points. So we're going to want to filter those out. One slick thing about our analysis is all of our point measurements are cached. So let's open up our point browser. And we have our three fields. We have our label, the deviation, and the inside, outside, or in spec field. And all of these can be sorted. So what I'm going to do is just click on this, sort by the largest numbers first, because I know they're all going to show up there, and it's an obvious cutoff right here. So what I'm going to do is just click delete. I'm going to get rid of those entirely, so they're gone. If I zoom in there, you won't see those points. And let's just rerun the coloring. So again, all of the results are technically cached. So all we're doing is rerunning the coloring of those. And so here they're all outside points, and they all seem to be relatively along the same band. And so that's all for this. You would generate your report, hide or show whatever points you wanted using the point browser, that's pretty much all for this example. I just wanted to show this particular one because it had the coordinate system in there, and that it's really easy to filter out noise data. So let's go to the next type of point, and this one is a more dense point set, so more along the lines of, say, a laser scan. So in this particular case, our source surface that we're bringing in is an IGES surface. So again, it doesn't have that it's not going to have that coordinate system because that format doesn't support it. And again, I can't remember if these are inches or millimeters. I think they're millimeters, but we may need to re-import them because it's not included in this particular CSV file. In fact, this is all we see. So let's bring those in. And what I'm going to show with this particular case is once you have a large data set, oftentimes, even though the analysis is very fast, if you get into the 50, 100,000 points, sometimes that density doesn't do anything like any other analysis. It's just added work for the processor and added time, watching paint dry as the user. And it doesn't really affect the end result of the analysis. There we go. So exactly what I expected. This was a millimeter point set. So you'll notice this. This is good to see what what happens if you didn't key in the values correctly. My scale was actually at inches, so I should have had this changed to inches. Again, this is just up to the user to know where they measured those in at what scale. So essentially, you just have to change your value and re-import. There's our surface. no WCS, and I know that they're measured at the origin, so I'm going to import my points. And it's a CSV file. And again, so this one, what I'm going to do is, it's interesting also, these points, when you're dealing with the surface, are only going to show up as being outside. You will not get any inside measurement. We will have, in the future, the ability to detect surface normals when you're not working on a solid model. Because with a solid model, you know inside and outside. You have a contained volume. But with a surface model, we detect anything outside of that surface as simply an outside measurement, even if it's on the bottom side of the surface. So again, in the future, what we'll do is take into account the surface normal, and if it's the reverse of the surface normal, we'll consider that an inside. But currently, what you're going to get is outside measurements. And so here we see that now they're laid on top of the surface as we would expect. So let's analyze. And you'll notice that the analysis is still very, very fast. And so it doesn't really affect performance too much, although when you have 50,000, 100,000 or more points, you'll see a difference. But right now we're calculating. And of course we color all the points based on their inside or outside value. Here again, because we're dealing with a surface, they're all outside. And these green sort of serpentine bands, this is where, Larry from Adaptive actually did this sample. This is where the points go inside. They pass through the surface, and so there is a period where they pass through the surface that they're actually in spec. But what I wanted to show with this example is the point thinner. So this is a very simple interface. You can reduce your point count by a percentage value. So 50% might be adequate in this case. But just to show you, let's crank it up to, say, 90% or 95%. Now, that's a little bit aggressive. You wouldn't normally be doing that, but what you'll see is it happens, very quickly. The analysis is going to be affected by cutting them out 95%, but it's just a tool to show you that you can very quickly reduce the point count using the point thinner. And so with that, because we have time constraints, that concludes point to part. And now let's get into a couple part to part. So this is our next category. We're going to do two styles. One is a validation, so a translation validation as per that AS9102, or D65991 rather. So let's bring in a couple parts. And again, this is validation. I'm going to show you one good and one bad. And of course, these are canned because many times they're good, and we'd have to go through a lot of them to know which ones those were. So we're going to use the same part, and I've changed the surface on the bad example. So this is a SolidWorks native file, and it was saved out as a step file. And so the derivative work, I guess you would call, the derivative is the step file, and we're going to run a validation. So a couple things first. This really, you don't notice it much on a validation because what you should hope to see is that all of the parts are actually the same. But notice this little, what we call a node control here on the bottom. When it's pointing to the source, that means we're looking at the source file. We're rendering and looking at the source file. We actually overlay the two parts on top of one another. And so if we click on the target, we're now rendering the target file. But again, they should be identical, hopefully, in a validation, and so you don't really see much difference. The next example, you will see a bigger difference. When I go to run my analysis, the same thing. Open your user input dialog, input your information. It stores each different report type. You can store different type of information. And so I put NASA here instead of my default TransMagic. And next we're going to check the validation button because a lot more properties get calculated on a validation. So we're measuring volume, center of gravity, moments of inertia, surface area, surface count, doing a geometry analysis. A lot of stuff is happening with validation, whereas revision, we can cut a lot of that out because we already know it's changed. There's no reason to calculate or spend all the time calculating those other properties when we know there has been a change. So let's run our analyze. And because of all those extra properties, as you might expect, the validation style part-to-part check takes a little longer. And what I'm going to show you here when this process is done is you're going to see this this part zoom in to the change regions if there are any. The green surfaces here indicate surfaces that haven't changed, so it kind of gives you visual feedback while it's processing. And it will continue to build those, so it's looking good at this point. And this is what you're hoping for. So if you're doing work for a large aerospace company and you have created a derivative and you're going to use it in your process, this green check is exactly what you want. So we'll click OK there. The find next change, there is no change, so nothing is going to happen in this particular case. We automatically populate the views in that view browser with the change regions, and so there will be no additional changes here. So for this particular part, let's just say I'm going to do a quick report. It's valid. I don't want to fill it up with a bunch of views. I'm just going to take my standard isometric view there, and I've already input my user information, and I'm going to create a simple report. Let's put this on the desktop. And there's just going to be, your default view and your isometric view. So let's take a look at this. And this is the type of report you're going to want to store, in your catalog for working with that large aerospace vendor. Notice it's changed up here, part-to-part analysis report rather. And you want to see these two check boxes. And so we do two sets of calculations. We've got our properties analysis, which is volume, center of gravity, surface area. We've passed all of these checks. And then the more comprehensive validation is our geometry analysis, which literally compares and runs a number of things on each surface to make sure that they're within spec. Because a typical volume comparison deviation will be 1%. But you could still get a pass there and a fail in the geometry analysis. And so the report simply catalogs all of the properties that we've calculated. You've got your source and your target, the percent difference, and a pass or fail. So here we have surface, volume, center of gravity, et cetera, and then on to where are our topology checks. So this is where we calculate the number and types of surfaces. Now topology, it's good to know, but it's something you don't want to put a lot of weight into. For example, when we're going from a native SolidWorks file, this applies to CATIA V5 also, they deal with periodic analytics. So these are spheres, cones, torus, cylinders as whole cylinders, or whole periodics are called, whole spheres, etc. No seams. When you save a file out to STEP, the STEP format requires what's called a split periodic, and that basically just means the surface needs to be split at 0 and pi. It is not it's not a quality thing. It's not an issue whatsoever. But what you'll see when you're saving out to STEP is a growth in your periodic surfaces because the count has increased. So everything is fine. It's just that you have more surfaces because STEP requires them to be split. So this is what topology checks gives you, is that type of information. But again, it's good to know, nothing you want to really lose sleep over. And then of course our views. We've got our a picture of our source, a picture of our target, our isometric, and that's it. So then we would simply store this report in the case of any future potential audit from our large vendor, or large customer rather. And so that's the validation style report. Next I'm going to do a revision style report. Oh, I wanted to show you a fail, but we'll do this here anyways, the case of a bad surface. But I want to keep conscious of our time and question and answer. So if you would have seen a fail, you'd get an exclamation point. We're going to do this in this example anyway. So we're going to start out here with a revision style report, and these are minor changes. Not a lot has happened to this particular part. Again, these are native V5. This is a landing gear strut, real world part. And what we're going to do now is check or highlight the revision radio button, and what you're going to notice is this calculation goes significantly faster. A pure revision calculation also, again, assumes that something has changed. I know that these little flanges have changed, these little mounting flanges here. So I'm coloring the source. Now it makes more sense when I color the target. You can actually see, I guess it's still hard to tell the change, but you can see them move ever so slightly. Bigger changes are more obvious. But so now let's run the analysis, and this doesn't do a gradient shading. This is for a revision, it's pure, it's what's called Boolean rendering, and it's true or false. Has this surface changed or not? In this case, you'll see green or red, and that's exactly what it does. The last phase will actually populate your views, so your change region views. There we go, we're generating our change region views. So something has changed in each one of those. And let's take a look at them. So let's zoom in. And I'm just going to turn my edges off, a little cleaner output. So all of the red surfaces have some sort of change. And let's just click Find Next Change Region. What that'll do is zoom in. So here we have the region involved is this red and green area. So the diameter or something here has changed. And actually, this angle, you'd have to turn it into wireframe mode. This angle is zooming in on the counterbore or the drill depth here. That's changed. Another one. And finally, it groups all of these flanges together because they're all connected. So if your surfaces are connected, like here, it considers this whole thing one change region. Also the last one is in there. This is, since these are all connected, these have all changed somewhat. This is the change region also. So one thing I like to illustrate, though, is that sometimes you may actually want to do a validation style analysis even though it's a revision. And so here's a reason why. When we have big changes, you're going to get, like in this particular case, when we do the source to target node control render, you're going to see visibly lots have changed. So these are going to come across as one change region, but we may want to catalog more information than that. So sometimes, even if you're after a revision check, you want to run the validation, and here's why. So in this case, we're rendering the source. If we click on the target, we can see that the head of this little part has moved out some distance. So we know we're going to find that, but we want a more comprehensive analysis of that. So let's change to validation. It's going to take a little bit longer, but let's run it. And if the surfaces have not changed, it actually is very fast. If they have changed, then it requires further analysis. So sometimes, if you're, it's working on a part that obviously nothing has changed, an area of the part, you'll just see the progress meter slam to some percentage value. Whereas if it is working on a change region, it's gathering a lot of information on that region. And this one actually does operate pretty quickly. Here in the green, we see that we have a lot of unchanged surfaces, but just visibly we can tell we've got a lot of changes. And this one I won't bother creating a report. We did that last validation report. It would be a similar scenario. And then that will leave us some time after this to show you an example of some translation using the IGES and step read capability, or save capability rather. All right, so we're just about done with our analysis. And again, the fewer the changes, the faster it goes. And what I'm doing is a color mapping. We have different rendering styles. So this one's going to be a typical color mapping. In the MagicCheck settings area, you'll probably want to play around with the different rendering styles. One really slick rendering style is called dot rendering. And it's a very bright, vibrant display. And good for generating graphics and reports and that type of thing. All right, just about done here. So the unclassified surface analysis is this is checking for surfaces that have moved so far that we're determining if they actually were changed or if they're actually new surfaces. And we can detect for those types of surfaces also When we have really drastic moves, the unclassified face analysis takes a little longer, just simply because it's trying to determine if they're new or not. So technically, because this had so many changes, it's called one change region because it really affected most of the surfaces. So again, we're running a validation here, so of course we have discrepancies, but we're doing this on purpose. I'm going to close down my views and show you some of our measurement tools on how you can sort of quantify what's changed. And so we can tell the direction of movement by the red and the blue rendering. So it's red on the back and blue towards the front here, and that is because it's moved in that direction. You know, again, those represent inside and outside dimensions. But what if we're concerned with how much it's moved? So let's take a measurement there. So we'll turn on our interactive dimensioning. Let's pull, I got to click and drag rather. So click and drag from this location to this location. So it looks like it's moved 0.118. And we'll just, to make sure this hasn't grown, let's try that here also. So, okay, so it looks like we've got a move of that, that head portion about 118. Another slick tool is, let's move to this area here. And, you know, this is shaded strangely. The other side of this little clamp region is green, so it means it hasn't really changed. But so what's changed here? Let's zoom in. And you can see on our overlay something has changed. Let's color the target. One of the nice features is let's turn off analysis shading. So the green surfaces are always, you know, unchanged, but something has changed here. Let's color our target. And notice how it's sort of the target, the change is bulbous there. It's kind of moved out from what it was. And so that's a very specific change to that region for some reason we don't necessarily know, but we have this neat micrometer function. And so what this does is if you click on the area of change, it will give you the measurement from the source, the measurement from the target, and that's thickness of each one of those, and then the difference. And so let's move it down here, and then you can kind of reposition that display. And let's do, looks like this has changed a little more here. And it's all dynamic, you know, it updates as you move your micrometer around or drag your mouse. So if I move it over here, I'm going to get, you know, close to nothing. There we go. And so that's just a way that you can sort of annotate some of these changes. So we've got a head move of 0.118, and I apologize, my graphics card for some reason always wants to draw my panels here in front of my part. We're looking into that. They should be actually rendered behind the part, just like we see these annotations there. But so it's a nice way to sort of categorize your changes. And let me do a time check here. So that's point to part and part to part. So that's the validation and then the revision portion. And so that really covers the core functionality of MagicCheck. And I just want to real quickly show, along with MagicCheck, you do get some other capabilities that are just more along the lines of translation. So here on our Home tab, let's bring in just a native, I'm bringing a sample file here. In this case, I'm just picking an inventor assembly. Again, native read. When you load a file into Transmagic on just the pure translation side of things, what will run is this auto repair wizard. So this is sort of a geometry health check. This is not along the lines of those validation checks or anything. This is just pure translation. We want a green light. We get a green light. We know that our part is good. We're ready to save it out. And your formats that you'll have available are STEP and IGES. So let's save to a STEP file, put it on the desktop. Simple as that. So you've got a STEP and IGES output, click and drag interface, you know, very Windows, very native. I'll drag it back in there. You could actually run a validation on those two parts. This is interesting. Notice the split cylinders just because it's a STEP. But so that's an example of a STEP translation. And let's take a look at something a little more sophisticated. Let's bring in an IGES file. And this is just a little dabble into our repair. We actually do a lot more if you have a full Transmagic license. One thing about an IGES file is that an IGES file is composed of surfaces in almost all cases. In this case, we get a yellow light. TransMagic reports we have 83 unstitched entities, so that's our surfaces. And all you need to do as the user is simply click Perform Recommended Actions. And that will stitch and find the solid volumes in your IGES file. So now you're ready to save that out. So instead of surfaces, we now have volume. The other thing here is it's an IGES model, so all we've done is stitch this together. We have not done anything to change the quote design intent. However, because it's an IGES, all of these surfaces are actually, in most cases, again, not all but most, spline surfaces. So even though this looks like a plane, this looks like a torus, a cylinder, they're all spline surfaces, and they have this split periodic. Let's say we're going to bring this into Mastercam or some machining application. It's not going to be able to detect cylinders or hole diameters because they're splines. They're not real holes. So one thing you can do as a secondary operation, if you want, is run light repair on the solid. And let's just pull off a dimension here real quick. Let's see, we'll grab an edge. And so notice how right now, because it's not a diameter, it just simply gives us a point-to-point measurement. So that's the best it can do. But if we run light repair, we're actually going to go, it's a more sophisticated operation called simplification. It's going to go and replace those surfaces that should be a plane with a plane, and cylinders and cone, torus, etc. So notice how my seams have now disappeared because they're real cylinders. And if I go to measure them, I'll get an actual radius dimension because it's now a real arc. So one more time, I can save this out to STEP or IGES. And it's as simple as that. So with that, and again, time being a concern here, I just wanted to make sure I showed that. We will go to our question phase.